Okay, so we have one last example to do. And this one is just kind of an application problem. It says we're looking for the average distance from a point in a ball of radius A to its center. So we mentioned a little while back how to find the average value of a function where the function is a 3-variable function. So I'm just going to give a reminder of that. Average value for a function f over some solid e, it looks like 1 over the volume of the solid times the triple integral of f of x, y, z dv over that solid e. So really it's just evaluating a triple integral and then dividing by the volume. So in this case, the function that notice we're not given a function explicitly, but the function that we're integrating here is going to be a distance function. The distance from the center of this ball to any point in the ball. The easiest way to do this is to place the ball so it has its center at the origin. So if we draw a picture of this, z, x, y. Let's take a ball, the radius of A, and position it so that its center is at the origin like this. There we go, something like that. Okay, radius is A. If I were to pick any point inside this ball and measure its distance to the origin, that distance can be given if the coordinates of this point are x, y, z. It would be the square root of x squared plus y squared plus z squared. We know that would be the distance. But since we are working with a sphere and we're talking about a distance, which is what rho represents, distance between a point and the origin in spherical coordinates, this is much better handled in spherical coordinates. So that distance right there is what rho would represent. That means rho is the function that we want to integrate here. So that's what we're going to do. Now, let's begin by finding a description for this solid E in spherical coordinates. Remember, E is the set of all rho theta phi such that, now let's think about the restrictions on each one of these variables. So rho, remember this is a ball, so it's dense, it has points on the inside. The distance from any point inside this ball to the origin is going to be less than or equal to A. Or another way that I can say that is that rho is between 0 and A. Okay? Now, just like the previous example, theta is going to be between 0 and 2 pi. There's nothing putting any kind of restriction on the theta. Again, I can take this point here, swing it around in a circle centered at the z-axis, parallel to the xy plane like this. So basically that's just letting theta go from 0 to 2 pi to swing that around. The entire circle would be contained in that ball. So this would describe all of those points. And then phi is going to be between 0 and pi in this case. In the case of a cone, like in our previous example, the edges of that cone represent the bounds on phi, essentially. Phi can't go past that. But in a sphere like this, the angle that this little line segment creates with my positive z-axis can go anywhere from 0 all the way to pi. That's as big as phi can get, is pi. So this describes this region. Now the next thing we need is the volume of this solid. We don't need to handle this volume in spherical coordinates as a triple integral because it's just the volume of a sphere, essentially. We have a formula for that. The volume for a sphere is 4/3 pi r cubed. In this case, r is a, so it's 4/3 pi a cubed. Okay, or I could also write that as 4 pi a cubed over 3, same thing. Okay, so now let's see what this would look like in our average value formula. I want the reciprocal of that volume. So the average value I'm looking for now is 1 over 4 pi a cubed over 3, or the reciprocal would just be 3 over 4 pi a cubed. Now let's look at the triple integral. Well, I used this this set to determine what the limits of integration are going to be. And remember, we integrate on the outside with respect to phi. So phi is going to be 0 to pi, followed by theta, 0 to 2 pi, followed by rho, 0 to a. Okay. The distance from any point here to the origin we said would be rho. And then we have to multiply that by rho squared sine of phi. So again, we end up with this, rho cubed sine of phi d rho d theta d phi, like this. Just like the previous example, I can break this down into 3 integrals. So I'm going to have 3 over 4 pi a cubed, integral from 0 to pi of sine of phi d phi. And then I'm going to have 0 to 2 pi d theta and 0 to a rho cubed d rho. Okay. Evaluating these, 3 over 4 pi a cubed. Just going to separate those. So this integral right here is going to become negative cosine of phi, 0 to pi. We know what this is going to be, 0 to pi d theta, that's going to be 2 pi. And then here we end up with rho to the 4th over 4 from 0 to a. Now there's going to be a lot of things that cancel out here. So if I begin by evaluating this guy, negative cosine of theta from pi to 0, that's 2. I'm going to get 3 over 4 pi a cubed times 2 pi times, this is going to be a to the 4th over 4. Okay, you should see a lot of things canceling out here. So the 2 times pi will cancel with the 4 pi here. The a cubed will cancel with all but one of the a's here. This leaves me with 3/4 a, and that's it. Okay. So that's all there is to it. Now that would have been really difficult to do with in rectangular coordinates. Not necessarily impossible, but this definitely simplified that process. So again, one more application where spherical coordinates are really useful. One thing that you're going to have to start to get kind of used to in problems like this is deciding which cases do you want to use spherical coordinates, cylindrical coordinates, or rectangular coordinates. And for spherical coordinates, oftentimes you are going to be using spherical coordinates when I'm looking for a particular page here. Here we go. Where the region that you're integrating over, the solid that you're integrating over, includes things like either spheres or cones, because both of those are very easily described in spherical coordinates. Sometimes even if you see half planes, that's again, those are constant functions as well in spherical coordinates. So those are indications that spherical coordinates are a good system to use. Cylindrical coordinates, as the name implies, cylinders. If a cylinder shows up in the description of the solid that you're trying to integrate over, then cylindrical coordinates is probably going to be a good approach. Also, because of this conversion formula right here, x squared plus y squared plus z squared, if this shows up either in the integrand or the description of your solid, this converts to spherical coordinates really nicely. In the last example that we did, we used spherical coordinates because the square root of this is what the distance from the origin to a point looks like in rectangular. So oftentimes if we're dealing with some kind of application where we're talking about the distance between points in the origin, spherical coordinates are a natural approach to take there. That should be it for 15.8.